Hey there, and welcome. You ever feel like the language of physics is, well, designed to be confusing? You hear words like velocity, acceleration, displacement, and it just sounds like a lot. But what if I told you that getting a handle on all of it really just comes down to answering two very simple questions? Well, that's what we're going to do. We're going to break down the physics of motion, so let's jump right in.
But first, let me ask you something. Imagine you just ran a full 26.2-mile marathon. You are completely exhausted, you've crossed that finish line, but in the eyes of physics, it's possible you've gone absolutely nowhere. How on earth is that possible? It sounds like a trick question, right? But the answer is actually one of the most important ideas in all of motion. So here's our game plan for getting to the bottom of this. We're going to start with the two basic ways physics measures anything. Then we'll use that to see the difference between a journey and a destination. From there, we'll talk about going fast and which way you're going. Then we'll see what it really means to accelerate. And finally, we'll tie it all together by learning how to tell the whole story of a trip with just a single graph. All right, so our first stop is to figure out how physicists even measure things in the first place. And it turns out everything we're about to talk about boils down to two simple categories, things called scalars and things called vectors. Trust me, getting this one concept right is the key that unlocks everything else. Okay, first up, the easy one, a scalar. A scalar is really just a simple number with its unit. You know, when you say you walked 5 meters, or the temperature is 20 degrees Celsius, or a car is going 60 miles per hour, you're using scalars. They only tell you one single thing, how much. But this is where it gets interesting. What happens when we add just one more piece of information? Direction. Well, that gives us a vector. A vector has that same number, that magnitude, but it also tells you which way. So it's not just 5 meters, it's 5 meters east. It's not just 60 miles per hour, it's 60 miles per hour north. And that's really it. That's the core difference right there. A scalar gives you the magnitude. It answers how much. A vector gives you that same magnitude plus a direction. It answers how much and which way. This one simple idea, just adding a direction, is what we're going to use for everything else we talk about. So let's put this new idea to work. We can use this whole scalar versus vector thing to look at our first pair of motion terms, distance and displacement. And this is exactly how we're going to solve that marathon riddle. To make this super clear, let's just imagine a really simple everyday story. Picture this. You walk out your front door, you go in a straight line to a coffee shop that's exactly 1 mile away. You grab your coffee, and then you turn right around and walk the exact same path back home. Let's start with distance. Distance is a scalar, which means it couldn't care less about direction. It's just the total amount of ground you covered. Think of it like the odometer in your car. Every single step you take just adds to the total. It only goes up. So back to our coffee shop trip. Your distance is pretty simple, right? It's 1 mile to get there and 1 mile to get back. Your total distance traveled is 2 miles. See? Easy enough. But now, let's talk about displacement. Now, displacement is a vector, so it's all about direction. It doesn't care about the winding path you took or how many steps you got in. It asks one simple, ruthless question. What is the straight line distance and direction from where you started to where you ended? So think about our trip. You started at home and you ended up right back at home. Your starting point and your ending point are the exact same place. So the change in your position, your displacement, is 0. Nothing. And there you have it. That's the answer to our riddle. You can run a 26.2-mile marathon, cover a huge distance, but if you end up right back where you started, your displacement is 0. You starting to see the pattern here? Scalar versus vector? Well, we're about to see it again with our next couple of terms, speed and velocity. And now that you've got the first pair down, this one's going to be a piece of cake. So, speed. This is the one we use all the time in everyday life. It's our scalar. It just tells you how fast you're going, how quickly you're covering that distance. When your car's speedometer says 60 miles per hour, that's your speed. It has no idea if you're going north, south, east, or west. Velocity, on the other hand, well, you guessed it, that's our vector. It's just your speed with the direction tacked on. So when a weather forecaster says a hurricane is moving at 20 miles per hour to the northeast, they're not just giving you its speed, they're giving you its velocity. So that's really the big takeaway here. Speed is just the number on your speedometer. Velocity is that number plus the direction you're headed. And this is why you can have a constant speed, but have your velocity changing all the time. How? just drive in a circle. Your speed might be locked in at 60, but since your direction is constantly changing, your velocity is too.
You know, that idea of a changing velocity is the perfect lead-in to our next big concept, because anytime your velocity changes, I mean in any way at all, you are accelerating. But what physics means by the word acceleration is probably a little bit broader than what you're used to. Okay, so here's the official definition. Acceleration is the rate of change of velocity. And remember, since velocity is a vector, it has both speed and direction. That means there are actually 3 different ways you can change it. And a change in any of those 3 things counts as acceleration. Just think about being in a car. You've basically got 3 controls that all cause acceleration. There's the gas pedal, which speeds you up. That's acceleration. There's the brake pedal, which slows you down. Yep, that's also a form of acceleration. And then there's the steering wheel. Even if your speed doesn't change one bit, the moment you turn that wheel, you change your direction. And since you changed your velocity, you, my friend, are accelerating. All right, time to bring it all home. For our final section, we're going to take all these ideas, displacement, velocity, acceleration, and see how we can tell the complete story of an object's motion using one simple tool, a graph. Now, this might look a little technical, but this is one of the most useful tools in all of physics, a velocity time graph. It's actually really simple. The up and down axis shows velocity, how fast you're going, and the side-to-side axis just shows time passing. By drawing a simple line on this graph, we can tell a surprisingly detailed story about a journey. So, how do you actually read this story? How can you look at a simple line and figure out if something is speeding up, slowing down, or just cruising along at a steady pace? Well, it's all about the shape of the line. If you see a perfectly flat horizontal line, it means the velocity isn't changing at all. That's constant velocity, 0 acceleration. But what if the line starts to tilt upwards? The steepness of that line, what mathematicians call the slope, that tells you the acceleration. A really steep line means you're accelerating fast. And one last cool trick. The total area underneath the line you've drawn actually tells you your total displacement, how far you've ended up from where you started. So let's end with one last brain teaser to lock all of this in. A car is driving on a perfectly circular racetrack. Its speedometer is glued to exactly 60 miles per hour, so its speed is totally constant. My question for you is it accelerating? Based on everything we've just talked about, you absolutely know the answer. I'll leave you to think about that one. Thanks for joining this explainer.